Welcome to Dr. Neutron, Physics After Midnight. While I regret not being able to make it to Fortnite Happy Hour, unfortunately, it took me a long time to get my son to bed. So instead, I thought I would make some physics videos. That's like the next best thing to playing video games. Let's take a look at problem number 41 from chapter 27. Problem 41 says, in figure E1, in the figure, we have one battery with, we have two batteries with different voltages, one at 2.3 and one at 8.5 volts. Then we have the circuit shown here with three different resistors, and both batteries are ideal, meaning there's no internal resistance. So what is the energy dissipated in R1, R2, and R3? And what is the power in each of the batteries for E1 and E2? So let's start by drawing our circuit diagram and then writing down the most important equations for this. I always like to draw pictures. You probably already know that, because it really helps you to understand the problem better. I really think that making a diagram helps you internalize it. At least it does for me, because I'm a very visual person. Okay, so our circuit is going to look something like this. We're going to have our battery here, positive, then our resistor, then another resistor here, and we're going to go like this. So here is E1, E2 is over here. There's our circuit, right? And now we've got our resistor over there. So there's our complete circuit. This guy up here is going to be R1. This one is R2. And over here we've got R3. Okay, well, let's talk about currents. We've got a junction here. So one thing to keep in mind is that current will always take the path of least resistance. So as current is flowing out of here, okay, as we go across a resistor, this would be like going up a hill. Okay, it would be hard for the current to go there. So it'd make much more sense if the current comes down here and it combines at this junction. Okay, so it goes in there. We're going to have a current. We'll call this I1 that goes through resistor R1, and then we'll have a current here, I2, that goes through resistor 2, and then over here we'll have a current I3 that flows through this resistor. Now, let's pretend that we don't know which way the current is going, just for the sake of argument, because it's more of a challenge, because we'll say maybe this circuit we can't really tell ahead of time. So we'll have I1 plus I2 plus I3 equals 0. So what this is saying is that if we add up all of our currents, then we better get 0. So the current going into our junction equals the current going out of it. And we don't know the direction of the current, so we're just going to say this. Okay. So let's consider here the left-hand loop, and we're going to go around our loop this way, okay? And down here, now it looks like right here that our currents flow into this junction, they go down here. Current's going to be passing through this resistor in one direction. there's no way that it would be going up because we don't have anything positive down here. So it would be crazy to say that. So let's modify this equation and say that the current going into our junction right here has to equal the current going out of it, because it would be insane to have current flowing backwards through this junction. So I'm just going to cross this one out. I1 plus I2 equals I3, because up here we're at a situation of higher potential and this is lower potential. So current has to be flowing this way through our resistor. This is the only thing that makes sense. I can't in good conscience write down this equation. It hurts me. Okay, and it's after 1 a.m. So we're just not going to do it. Let's think about our loop here as we go across this first battery here. We're going to move in the direction of current. So we're going to have E1 here. Then we're going to go across this resistor in the direction of the current. So minus I1 times R1. And remember, as we go across the resistor in the direction of current, we're using the loop rule, we get a negative sign right here. Now we go across this resistor and we're going in the direction of current again. Now we have minus I3 R3 equals 0. This is from the right loop. No, the left loop. The left loop. There we go. That is from the left loop. Then from the right loop, we're going to do the same thing. We're going to go across this way. We're going to move around. This time we're going to go counterclockwise. It really doesn't matter, because whether you go clockwise or counterclockwise, because all of the signs will be opposite either way, so it doesn't really matter. Okay, so we're going to go up E2, so that's going to be positive. Then we're going to go across this resistor in the direction of current, minus I2 times R2. Then we're going to go down here, so we'll have minus I3 R3 equals 0. Okay, so we have our system of 3 equations here, and we're going to need to know what all 3 currents are. We can do that now because we have 3 equations and 3 unknowns. So we can solve for I1, I2, and I3 with some algebra. But now the question asks, what is the energy dissipated in each of these? So we are going to use the equation for power for a resistor, and we know the current and we know the resistance. So going through the resistor, then the energy dissipated is going to be I squared times R. And if we want to know the energy being or the power output from the battery, then we're going to use P equals I times V. There's no resistance in these because they are ideal batteries. So once we know each of the currents, then we can say, okay, I1 is coming out of here. So that's our current coming from the battery. So once we solve for I1, I2, and I3 using these 3 equations, then we can now use these to get our final answer. And I'm not going to lie, there's some significant algebra, but it's once you get through all of the algebra, then you plug in your numbers, and these are the equations that you are going to use. So this is how you set up the problem, and then these are the 3 equations that you start from, and then you should be able to get your answer.
Thank you. Like and subscribe down below.